So let's talk about these because we have the final on Monday, so like a week and a half. Number one thing to do, which you could do at the beginning of the quarter, and then like try to do it the whole thing. But especially when you've only got a week and a half to get ready, make a schedule. And when I say make a schedule, I mean account for every hour. Like when you're going to sleep, when you're going to eat, when you're going to be in class, when you're going to be at work if you got a job, when you're going to chill out, hang out with friends or watch a TV show, when you're going to study. And I also strongly encourage that you plan a snack time before your study time. Because there's nothing worse than sitting down to start studying and then you're like, oh, I'm hungry, and you can't focus. So especially if you've only got like a week and a half to get ready for the final, make a schedule, do your best to stick to it. The big question becomes after you've got that schedule, what do you do with your time when you are studying? And there's a couple things. Thing number two is how to use the textbook. And using the textbook is different depending on what class you're studying for, what subject you're studying for. In chemistry, there's a couple important things. Chemistry is kind of a weird class because it's like a language class and a math class mixed together, right? It is essentially all word problems all the time. So one of the main things that we have to do is make sure we're good with the key terms, the vocabulary. So the back of each chapter has a list of important vocabulary for that chapter. We want to make sure that we're familiar with those, that we can know how they interact with each other. We want to know the definitions individually. And we also want to think about how the different terms relate to other key terms. If you've got enough study time, you can make a relation map. That's essentially, you can write down, if you wanted to put something big at the center for our class, for your relation map, you can put equilibrium in the middle, and then all the things that relate to equilibrium, right? What are the other terms that relate to equilibrium? What are the key problems that do equilibrium? You can start to relate to that. Someplace in there, you'll get stoichiometry and how that relates to things. You can make a key term like a relation map. Because one of the problems that we have with chemistry is, and this is also part of the problem with using the textbook, is it's not a linear story like a lot of other classes. You know, if you're in a history class, you start at one period in time, you go through your periods in time. Chemistry is like a jumble of string, and each subject touches another subject. So we kind of follow one strand for a while, and then we hop over to another strand and follow it back, but everything's really interrelated. So getting a really key terms of relation map. You also want to look at chapter summaries. The textbook we're currently using has chapter summaries, so each section has a section summary associated with it. And this gives you a way to get an idea of what the authors thought were most important in each section. A great example is if you look at chapter 15, one of the chapters that we've been doing a lot with acid-base chemistry, buffers, that chapter is 80 pages long. It's a really long chapter. The chapter summary is 2 pages. Now, obviously, if you're boiling it down to 2 pages, you're going to be missing some information. But reading the chapter summary before the chapter, because you should still read the chapter if you have the time. But the chapter summary will essentially clue you into what the author thinks are the most important things in the section. So that way, when you're reading the chapter, you're going to run into something and be like, oh, they mentioned that in the summary. I should probably pay attention to this. Versus the kind of more anecdotal stories they have to give you context for what they're talking about. Sometimes they'll go on a tangent about biologically interesting buffers. It's really neat. It gives us some context for us that are studying bio. And we're like, wow, this is really cool. It's applicable. But in terms of what we need to remember for the class, We really need to know how buffers work, not how they relate to biology, right? There's kind of the essential versus the more broad. So making sure we know how to use the textbook. Question, yeah.
So we don't have to know everything in the 80-page acid base chapter, do we?
There's a lot. Like we go over a lot of it. A lot of that 80 pages is sample problems that are worked out. There's a lot of images. There's a lot of titration curves. And a lot of that takes up space in the chapter, and it's stuff that we should know. But in terms of the text, you're not going to need to know every word in the text. But we've covered a lot of it. Keep in mind, we did that chapter over the last 3.5 weeks, 4 weeks. So 80 pages over 4 weeks is only 20 pages a week if we've been keeping up with the reading. So now let's get into, after we're kind of comfortable with the key terms and kind of the chapter summary and the concepts in there, we want to start working on the problems. There's a couple different things we can do. The first thing that I suggest that is probably the biggest time sink on exams. So if you're someone who's like, I just take tests slow, I don't know how to go faster, one of the things to practice is just how you approach the problem. That is to say, when we get a problem, we don't do the entire problem. We just kind of make a plan for how we would do the problem. Let's see. Does anyone have homework 6 handy?
I can pull it up.
So I want an example of what I mean. Let's see if I can remember one of the problems. So one of the problems is, let's do this in green. A quick example. This is problem 8. I did it in office hours earlier, so I think I can remember. What is the solubility
I have homework
of
7.
AgI in 600 milliliters of 0.91 molar NaCN? And then you're also given the Kf. I didn't give myself enough space. You're also given the Kf for AgCN2 minus is equal to, what's the number value for the AgCN2 minus?
For KF?
Yeah.
It's no.
Oh, it is. Okay.
Yeah.
Ready.
Oh, okay. 1 times 10 to the 21st.
Positive 21. So what we want to do with our approach practice is we don't want to do the problem. We just want to break the problem down, because one of the biggest things that slows us down on tests, and personally when I was taking tests and I would freeze on a problem, is when I read through a problem and I'm just like, I don't even know where to start. And one of the things that helped get me over my test anxiety was coming up with a systematic way where I could just break a problem down. So I look at this and I start to recognize the most important things. Solubility, right? I know I'm going to be dealing with solubility. I've got 600 milliliters of 0.91 molar. I've got a Kf, right? I find those key things. And then rather than going through and doing the problem, I come up with what do I think is going to happen? So one, write the reaction. You just come up with a plan. You're not going to do the problem. You're just going to figure out your approach to the problem. So that way, if you run into a problem where you freeze, you just kind of go to this, like, I'm going to systematically take it apart and think about it. I'm going to write the reaction. I've got some volume and some molarity, so I'm going to think that I'm going to do some stoichiometry. I'm not sure, so I'm going to put a question mark there, but I think I'm going to do some stoichiometry for that. And then, and that's also a fair guess because everything we do in this class, stoichiometry, equilibrium, stoichiometry, equilibrium. 3, I'm going to get my K reaction. I might need to do K reaction before 2 to figure out if it's going to go towards products or not. But I know that at some point I'm going to want K reaction before I do some equilibrium table. right? And I can look at this and I can say, okay, now I've got my approach. If I'm feeling a little vague, if I'm like, well, I don't really know what I put this because this is what I put for every problem. We want to put a little bit more detail. Write the reaction, say what the reaction is going to be. Write the reaction of AgI with NaCN to form the metal complex. I want to do the stoichiometry of how much metal complex is going to form and how much silver iodide is reacted. I'm going to want to calculate my reaction for the formation, for the breaking down of the solid and the formation of the metal complex, right? Add more details. But that gives us a way where we can kind of just get used to figuring out what we're going to do on a problem.
Wait, I have a question for you.
Yeah.
Do you not need KSP to solve this problem?
You do need KSP, right? You're going to need
Oh.
KSP when you're doing the K reaction, but you don't need KSP to just do the stoichiometry.
KSP be given?
KSP would be
Oh,
given.
okay.
I think, was it given earlier in the problem,
I
or
don't know.
you might just need to look it up, because on the homeworks, I assume you can look these things up. Now, of course, then we've got do problems. And I'm going to suggest this kind of in two ways. You're going to do problems alone. And you're going to want to do 3 to 5 problems at a time. One of the mistakes that a lot of people make when they're doing problems, especially out of the textbook, because the textbook has some answers, they do a problem and then they check it and they're like, oh, I got it wrong. And then they do another problem, they check, like, oh, I got it wrong. We want to do 3 to 5 problems at a time without checking it. We want to see where we get stuck, right? We want to start to recognize patterns in our own learning and our own shortcomings. If we're getting stuck at the same point every time, that's something we can fix. But if we don't know that we're getting stuck at the same point every time, we don't know that's what we need to fix. So we want to start creating places where we can find patterns in our own difficulties, right? We want to find out, oh, I'm always getting stuck when I'm flipping the reaction. So that's the one thing I need to fix, and then I can do all 5 problems. Rather than thinking you've got 5 unique problems to deal with, it turns out you've got 1 recurring problem that needs to be fixed. The other thing that I really suggest is group. And I've got a particular activity that I think is good in groups. So a lot of times when groups get together to study, you just kind of like, oh, I don't know, we're going to do the homework again. Or you're like, oh, I don't know, we're just going to like look at definitions together. And you get distracted. You know, it's nice to have a really clear kind of activity to do together. So the idea here is 3 to 5 people, and each of you are going to write a 4-question quiz. So essentially you want one that's easy, one that you think, one that you're like, I know the answer to this. Everyone should know the answer to this. 2 where you're like, I think this is challenging, but I'm pretty sure I know how to do it. And 1 where you're like, I don't even know if I can do this, right? You're going to write a 4-question quiz, and then you're going to pass it. You're going to pass it to your neighbor. You're going to get your neighbor, you know, you're going to pass them clockwise or counterclockwise. It doesn't matter. You're going to pass them. So that way you get a quiz. Now this does a couple things. 1, because you're getting a set of questions that you haven't already been looking at, you're short-circuiting the kind of picking that we do. When we work alone, often we'll unconsciously pick problems that we already kind of know how to do. We'll avoid the really hard problems. So having somebody else hand us problems short-circuits that. That's one thing that it does. So that way you're getting problems that you're not like subconsciously picking. 2, it gives you some idea of what other people think is easy and hard in the class, right? If they hand you a quiz and you can't do the first problem, that you need to be worried. But if you can't do the first problem, go back to doing the approach practice, right? Write down what you think is important. Since they thought it was easy, they should be able to explain it to you. And you get to see what other questions they think are important in the class, what they think is easy, what they think is hard, what they think is important. It also gets you into the mindset of your instructor, me in this case, where you now have to think, okay, what are the important questions? If I'm only going to make a test that's 4 questions, what 4 questions would I make? Right? I'm going to make one that I think everyone can do so that everyone gets at least 25%. Second one that's a little bit harder, so most people, like everyone should be able to get 50%. One that's a bit harder, so some people get 75%. And one that's really hard, so only the best students get 100%. Now, of course, I'm not going to just do 4 questions because that's not enough. There's not enough variation there. We're going to do a lot more questions on the final than just 4, but it gets us into that kind of mentality. We also are going to, make a quiz that we think we can do in 20 or 30 minutes. So we're going to get an idea of how fast we're doing problems and how slow we're doing problems.
How much of the final would you say is going to be like conceptual versus calculation?
Similar to the midterms. So, we're looking at, like if you looked at a free response problem, you had like 2 kind of conceptual questions, 2 calculational questions. If you're looking at the multiple choice, you get a lot of short conceptual questions that are kind of definitional, and you get a couple calculational questions. Yeah.
How many hours do you think we should be studying a day for this?
So the guiding principle in the College of Science and Math is 25-35 a week. If you haven't heard that before, 25-35 a
I don't
week.
think I've heard of it.
Really? Oh yeah. No,
Like
it's a pretty common thing. I've heard it mentioned once or twice in the department. I've got some magnets if you want, some flyers. So the idea is, if you look at high school, you're in class from what, like 8 to 4?
No,
8 to 3? I don't know. I haven't been in high school in a while. You didn't have a 7th period? I had a 0th
7th
period and a 7th period. Because I did sports after school, so.
Oh, yeah.
So you're in class for a certain number of hours a day, right? So is it 8 to 3 with an hour for lunch? So that's like 5 hours a day. I don't know. Essentially, you should be treating your college career as a full-time job, which means you should be putting in 40 hours of work a week, minimum. When you start looking at the amount of time you're in class a week versus the amount of time you should be putting in, you end up with 25 to 35 hours that you aren't putting in class. So that's where that studying comes in. The other guiding principle is 2 hours of studying per unit of class.
Yeah, it's like 2 hours per unit. Yeah.
So our chemistry class is 4 units. Yeah. So the lecture is considered 3 units. The lab is considered 1 unit. I think that's a little skewed, but if we've got 3 hours of lecture, if we've got 3 units in our lecture, you should be thinking 6 hours of studying a week. So at least an hour a day. You also want to think, when you're thinking about your study time, you really do want to think about what's your most effective study block. For me, 1 hour is too short, 4 hours is too long. If I try to study for a 4-hour block, the last hour I'm just kind of brain dead, not doing very much. If I try to study for 1 hour, I find I'm just getting going when the hour's up. So I usually aim for like 2 to 3 hour study blocks. That's for myself personally. Something might work differently for you.
One question. How is the final going to be all equal parts, like from each midterm?
It's cumulative. The stuff from the second midterm on, it's my only time to test you on it. So I'm going to have to get some stuff about ligand field theory and complex formations. Fortunately, as you can see, a lot of it relates to old material as well. So cumulative.
So it's equal parts everything?
Yeah, probably the best way to think about it is how much time did we spend on this in class? For example, ligand field theory, we're gonna try to do ligand field theory in 1 hour out of the 30 hours of class we had approximately. So you can imagine like 1/30 of the test would be ligand field theory. Now keep in mind, ligand field theory is going to relate to metal complexes, which we spent 3 hours on already. So, that could relate in. Ligand field theory is also going to relate to molecular orbital theory, which we're going to spend a couple hours on. So that kind of connectivity kind of short circuits that thinking, but that's generally the broad thinking we can do is how many hours do we spend on it in class gives us an idea of how important it is. So I try to spend more time in class on the things I think are more important. Question?
Is the format kind of the same as the other two midterms, like with the short free response, or short multiple choice free response, and then long?
Yeah.
So the same thing, just more of them?
Just more.
Okay.
Just more.
How long is it? How long will it be? Final?
Oh, I don't know yet.
Okay.
Probably 2 or 3 free response problems. One of them will definitely be a titration that you should all do very, very quickly.
By 2 or 3 free response problems, do you mean like
Like
1 or 2 like multiple part
Yes.
free response problems? Okay.
1 or 2 of my free response problems. So, any questions about these kind of like things for the study tips? Okay. Great.
I think I have the hardest time like preparing for the free response. I just don't ever know what to expect.
The free response is really
It's like
hard to prepare for.
it's like you have to be good at the conceptual stuff to be
Yeah.
able to do that.
So you notice in order to be good at the free response, you have to be doing 2, 3, and 4, right? It's a combination of all of these things. You have to get the key terms and the concepts. You have to be able to figure out the approach. And I find the hardest thing with the free response problems is the approach. Like if you can get through the words, because a lot of times I like to make the free response problems interesting. I like to make them relate to something. I like to bring in, DNA as a weak acid, weak base. I like to bring in water purification for competitive solubility. I like to bring in these other ideas to make it more interesting and to make it more practical, but it's not core to solving the problem. So figuring out what's necessary and what's not necessary, being able to rip through and being able to be like, this is what's important, this is what I think I'm going to do the problem. And honestly, just having that on a free response problem will get you partial credit. Like, I gave partial credit to somebody who just had the list of what they were going to do for part B of the free response on the last test. They put, I know I need to do this. They listed out exactly what they needed to do, but they didn't do it. They still got partial credit.
Do you think you'll make the free response something that we've never seen before?
Do you feel like the last free response was something you've never seen
Yeah.
before?
Yeah.
Then yes. It shouldn't have been something that you've never seen before because it was the Buffer's lab calculation, verbatim.
Oh, I don't know if you've like already gone over this in a video, but how are you supposed to get the information you needed to solve that problem with, you gave us 1 molarity and like the total milliliters that you had or something of buffer?
2 molarities. You had the molarity of the titrant, the molarity of the target molarity of the buffer, and you had the total volume of the buffer. So you had all of the same things you had in the Buffer's lab. It was exactly the same as the Buffer's lab, except for the word polybasic apparently just sent everyone into like a mind-blowing frenzy.
Was it a target molarity or was it like a
Total
this plus
molarity.
the total molarity is really different from target molarity. That's
Right. I called it the total molarity on the test.
But then how are you using that combined molarity or whatever you like call that, the
total molarity.
Total molarity. How would you find the molarity? Because I can't remember which molarity you gave me. There was the acid or the base, but how do you find the other one?
So I gave you the total molarity and the molarity of the titrant, right? The strong titrant.
Yeah, okay.
And then you do it exactly like the buffer setup. So you use Henderson-Hasselbalch to solve for a ratio. You use the total molarity to substitute in and solve for the concentration of each thing. You end up doing 2 equations, 2 unknowns.
Okay.
It was exactly the same as the buffer setup with different words.
Do you have it
So-
in one of your videos?
It's in one of the videos, and I can show you after we finish doing the
Okay.
study tips. So in terms of, did I show you something completely different and unusual that was like you've never seen before? Yes, but not really. And that's where the approach practice comes in again, right? Breaking down the problem. Where if you just broke down the problem and you said, I've got a total volume, I've got a target, I've got a total volume, I've got a total concentration, I've got a target pH. Once you break it down to that, hopefully if you've been doing your approach practice with your homework and things like that, you're going to notice and you're going to be like, oh, this is just a buffer calculation like the lab, or like the homework problem, or like the quiz, where we've done buffer calculations multiple times. But again, if you haven't been doing the approach practice and you don't know how to pull the problems apart, it's really difficult. So having the vocabulary, doing the approach practice is probably one of the best things you can do for the free response problems. There's also a theme, particularly to my free response problems. And I know some of the other instructors have things like this, but for my free response problems, I essentially try to take something that's exactly like we've done in class with a little tweak. And I want to see, can you deal with a little tweak or not? Because the best students that I expect to be getting A's and like B pluses can look at the little tweak and be like, whoa, this is kind of different, but I think it's pretty much the same. And they can deal with the little tweaks. The students who are having trouble with the conceptual relations, doing that kind of relation map and understanding how to break down a problem, they look at that little tweak and they're like, this is completely foreign and completely different. And that gives me really good insight to your capability with the material, which is why I do free response problems. So essentially, a way to study for this is when you're doing your group quiz pass, take a problem and just try to change it a little bit. So when you make these quizzes, you don't have to make up your own problems. You can take them from the textbook. You can take them from the homework. You can take them from the internet. You can take them from the lecture slides, the worksheets, any place. And you can also kind of just tweak them and make them like a little bit different and see if the person next to you can still do them, right? Because the only difference, so like I'll give you another example. What if I gave you a buffer, but it was at the second midpoint? All the calculations are actually still going to be the same, but we've never explicitly done something like that in class. And for this midterm that we just did, I was like, ooh, do I want to do second midpoint or do I want to do a base at the first midpoint? I went with a base at the first midpoint. I don't know how it would have been if I did a buffer at the second midpoint. If it still would have just thrown people off completely and they would have had no idea what to do, or if they would have been okay with it. Because it is one of those things where it's like, actually the calculation's the same, but it's just this little tweak that makes it so it's a little different, and I want to see how you deal with that. Any other questions, thoughts, ideas?
Will the final be more conceptual heavy or math heavy?
Yes.
Oh, so kind of split between?
Yes.
Okay.
Right, if you look at almost all of our tests, we have a pretty good split between the conceptual and the mathematical, because chemistry is a combination of those two.
All right.
Right, you do a bunch of math, and then I want you to explain the concepts behind the math you did. Like you do a buffer calculation, and I say, okay, explain whether you made good approximations or bad approximations. I had some people who were just like, I don't think I made any approximations. I'm like, no, you definitely did. So, we've got the concept and the math together. Okay, I gotta get ready for lab. If you have more questions, let me know. If you want more office hours before Monday of next week when my next office hours are, let me know. We can make